First of all, I would like to thank the organizing committee for giving me the possibility to present some of my scientific results using a video presentation, since I'm not able to reach the site of Congress due to coronavirus spread. I'm going to talk about a class of compounds, namely 1,6-naphthyridines, that from some preliminary screening recently performed proved to be endowed with antiviral activity against HIV-1 virus, but at the beginning of our studies they were investigated as promising photosensitizing agents. The therapeutical effect of light has been known for thousands of years, but it was only in the last century that PDT was developed. In 1993, the porphyrinic photosensitizer Photofrin was approved in Canada for the treatment of bladder cancer, and in the following years it received the approval in other countries for the treatment of lung, esophageal, head and neck cancers. Since then, new photosensitizers have been developed. Compared to other therapeutical approaches, PDT has many advantages, such as high tumor selectivity, low tissue toxicity, reduced long-term morbidity, and lack of acquired resistance. PDT requires three elements: light, photosensitizers, and oxygen. The photosensitizer must be inactive in the dark, but upon light activation at a proper wavelength, it goes from a ground state to an excited one. As it returns to the ground state, it releases energy which is transferred to the oxygen, thus producing free radicals and singlet oxygen, responsible of cellular toxicity. Activated photosensitizers can undergo two types of reaction. Type 1 reaction, in which they directly react with a substrate such as biomolecules or cell membrane to form ROS upon reacting with oxygen. Type 2 reaction, in which energy is directly transferred to the oxygen, thus forming singlet oxygen. Both types of reactions simultaneously occurs, and the ratio between them depends on the type of photosensitizers. Photosensitizers generally target mitochondria, lysosome, plasma membrane, and endoplasmic reticulum. Furocumarins are natural occurring photosensitizing agents extracted from more than 1,500 plants, and among them the linear derivative 8-MOP is one of the most widely used drugs. Differently from conventional photosensitizing agents, furocumarins act through an oxygen-independent mechanism. In fact, they can intercalate into DNA, and upon UVA light activation, they can give photocycle addiction to DNA, thus producing mono or bis adducts with DNA. And these latter are responsible of severe cytotoxic effects. Angelicin is a promising furocumarin, since, due to its geometry, can form only monoadducts with DNA. In this context, and considering our interest in the chemistry of pyrrole, we have synthesized several heteroanalogues of angelicin, and among them, pyrroloquinolinones that are nitrogen heteroanalogues of angelicin showed interesting properties, being able to photoinduce cell death with GI50 values up to nanomolar level and without inducing photodamage to DNA. Carrying on our studies, we synthesized new tricyclic analogues in order to explore the influence of the introduction of another nitrogen atom and also the annihilation with a thiazole or an oxazole and triazole ring. Therefore, both naphthyridines and naphthyridinones were synthesized through a multi-step synthetic pathway, and they were evaluated for their phototoxicity at the Department of Molecular Medicine of Padua. Antiproliferative activity was evaluated on a panel of 3 human cancer cell lines and 1 non-tumor cell line. Phototoxicity was expressed as EC50 values, while toxicity in the absence of light was expressed as CC50 values. Notably, no cytotoxicity was described in the absence of light. And among the 3 classes of compounds, triazolonaftiridines demonstrated phototoxicity with EC50 values up to nanomolar level. Among the thiazole series, compound 1F showed promising properties with EC50 values in the nanomolar range, but the most interesting compounds were oxazolonaftiridines, which were able to induce UV-dependent cell death with EC50 values from low micromolar to nanomolar level. The most potent compound proved to be derivative 2E with EC50 values between 10 and 12 nanomolar. It has also high selectivity index, which indicates tumor selectivity, and high PTI values, which indicates the effectiveness of the tested compound upon photoactivation. Thus, the most potent and selective compound 2E was chosen to investigate the mechanism of action of naphthyridines. Thanks to its fluorescent properties, it was detected using confocal microscope, and as can be seen from the blue signal, 10 minutes after administration it is well distributed into the cytoplasm, where it remained 30 minutes and 1 hour post-administration. No nuclear signal was ever detected, thus suggesting a cytosolic DNA-unrelated mechanism of toxicity. Production of ROS was evaluated through a fluorescent dye. Cells treated with ROS inductor, PMA, and light activated were used as positive control. 2 hours post-photoactivation, increasing concentration of 2E produced an increment in the fluorescence, which reached 227% of the untreated control at the highest concentration, a value much higher than 120% reached by the positive control, thus suggesting that 2E promptly and massively produces ROS in cells. To support 2E-induced ROS production, cells were pre-incubated with ROS scavenger and acetylcysteine, which significantly reduced ROS production in a dose-dependent manner. A copious amount of ROS can trigger cell death through different mechanisms. A cell death pathway was then evaluated. MCF7 cells were incubated with increasing concentration of 2E, and cell population analysis showed a high percentage of apoptotic cells and a small amount of necrotic ones, thus suggesting that oxazolonaftiridines can push cell population into an irreversible apoptotic process. Mitochondrial dysfunction and lysosome involvement were also evaluated, and with respect to the control, 2E is able to cause perinuclear mitochondrial clustering followed by organelle fusion and mild swelling 20 minutes after irradiation. And it is impressive considering that PMA caused condensation of mitochondrial network 6 hours post-treatment. Also, lysosomal activation was detectable 20 minutes after irradiation. Literature survey revealed just few examples of naphthyridines as antiviral agents. Thus, we were attracted by this repositioning possibility, and we decided to further explore this aspect. And once again, our compounds were tested at the Department of Molecular Medicine of Padua as antiviral agents against HSV1 virus. which is one of the most adept human pathogens infecting a high percentage of world population. It is a large double-stranded DNA virus whose genome is encased in a capsid, further surrounded by a lipid envelope, composed of different glycoproteins. Most of them are important in the initial attachment of the virus and entrance into the cell. After envelope fusion with the membrane, the capsid is transported into the nucleus, into the nuclear membrane, where viral DNA is released. In this way, HSV1 infects epithelial cells and establishes a latent infection in sensory ganglia, from where it periodically reactivates, causing recurrent lesions at the site of primary infection. It can cause both innocuous diseases such as herpes labialis or more severe diseases as encephalitis or blinding keratitis. Current treatment includes administration of nucleoside analogues such as acyclovir. All these drugs can limit viral DNA replication and suppressing the disease symptoms, but they do not fully suppress viral shedding, allowing the virus to persist. Thus, a long-term therapy is necessary, leading to development of drug-resistant strains. Therefore, has become mandatory to explore non-nucleoside cores in order to find new antipathetic agents. And in this context, we decided to test our tricyclic compounds on HSV1 virus lytic cycles. And from some preliminary screenings, it was possible to detect that compounds 3F and 4B had displayed a remarkable inhibition in the viral cycle with IC50 values in the nanomolar range with a high selectivity index. Disclosure of the mechanism of action is important to develop new drugs, and the time of addition assay is a well-known tool to establish the mechanism of action by comparing the TOA profile of novel compounds with that one of a well-known reference compound as acyclovir. Therefore, TOA assay was performed, and it was able to see that both 3F and 4B can hinder a HSV1 virus cycle in the pre-replicative stage. In fact, no reduction in viral load was detectable when compounds are administered from 8 to 6 hours post-infections, and it is an excellent mechanism to exploit to propose novel drugs able to overcome acyclovir resistance. In conclusion, starting from promising photosensitizing agents, we arrived at antiviral agents, and having found two interesting hits, we are going to explore the chemical space around these two entities in order to improve their potentiality with the aim to get to a lead. In the end, I would like to thank my research group, the colleagues of the Department of Molecular Medicine of Padua, and of course all of you for the kind attention.